Well, thank you for the opportunity to present today. As Guillermo said, I will be talking about Imagine, which is a summer school that was organized by CAMERA, the Consortium for Advancement of MRI Education and Research in Africa. And yeah, this is relevant to MRI accessibility for in terms of MRI education in low resource settings, as well as education from a more hardware side of things and specifically focused on low field MRI, which is also a very important point of care tool. So just to give you some background about CAMERA, for those that are not familiar with it, CAMERA stands for the Consortium for Advancement of MRI Education and Research in Africa, and is basically an organization that aims to improve, to democratize MRI in low resource settings through three main pillars. Those are optimizing infrastructure, training experts in place, and building collaborative networks within low resource settings, but also worldwide. CAMERA has a bunch of different initiatives, from which not even all are listed here. And they can be broken down into these three main components. And specifically for the training programs, we have Scan With Me, which is aimed at MRI technologists, so the people operating the MRI scanners. Spark, which focuses on AI applications, so mainly for post-processing side of things. In particular here, the participants train to participate on a brain tumor segmentation challenge from MICAI. Then we also have Connexin, which looks at the analysis side of things. So once you have acquired your brain data, in this case it's brain imaging, but in general it doesn't have to be. How do you use this for diagnostics, and how do you evaluate your data? And then the newest addition to the program is, wait, can you see my point?
Yes, we can see the pointer.
Okay, great. So the newest addition is the Imagine Summer School, which looks at the hardware side of things and low field MRI concretely. Then there's also programs aimed at data collection, mentorship, and also collaborative networks. The training programs all follow the same pedagogy, which is based on the RAD8 Teach, Try, Use. So essentially, the first block is building a foundation for the participants to get really familiarized with the program content. So this can be, depending on the program, it's 2 to 5 weeks of self-paced online content. So this can be anything from papers to YouTube videos to books. Then Try, which is mostly a 2-week seminar-based content. So these are experts in the field that come to present on a given topic from this course. And then comes the last part, which is the use part, where participants get to apply the knowledge that they have acquired in the program. Either, for example, in Scan With Me, this would be in terms of acquiring images on their own scanners. So the new sequences that they have learned or the new parameters, they can then play and apply these in their own scanners. Or for Spark, this would be participating in the brain tumor segmentation challenge. And then, as you can see on the left, this is a cyclical process, since the participants that are most active are invited to return the following year to train the next generation of trainees. So this not only allows the participants to get more comfortable with the content of the course, but also to make them confident in also sharing and spreading this information further, not only inside these courses, but also in their own context. Okay, so yeah, the teacher I used for each program will have a different focus. So, Scan with Me is aimed at MRI technologists, Spark is aimed at pretty much anyone with a computer science or um, AI interest, and Connection is aimed at clinicians and researchers. And for each course, obviously, the content will, within the same structure, have slightly different content. In terms of program outreach, you can see that with each consecutive year, the course size grows, the number of participants grows slightly bigger. So the biggest one by far is the Spark program. Um, and then the last program that was added, as I said, the Imagine Summer School, which took place for the first time this year, but we aim to expand it next year to make it a bit bigger and also hopefully have more people attending in person, which I will get to a bit later. In terms of geographical outreach, you can see here on the map the countries that have or are currently participating in programs, in any of the programs, as well as in purple, the collaborating high income countries. So on the back end of camera, there's a lot of people, more actually than the ones shown here, that are participating in camera to different degrees. Camera is primarily volunteer based, so due to limited funding, it's a cause that requires a strong community commitment. And the people that partake in camera come from a very broad range of different backgrounds. So some people can come from engineering, medicine, MRI physics, or MRI technologists. This is a global network, so it extends to Africa and beyond. And it's quite, for most people, it's quite project focused. So most people will choose to contribute to mainly one program, also oriented by their own area of expertise. And the ways of contributing consist either giving seminars, educational content, helping with organization and logistics, or with mentorship. Now, coming to the Imaging Summer School, which is stands for Imaging Without Borders. As I said, this took place for the first time this year, and it's a collaboration between the Neuro in McGill, the Mind Lab, MRI Uganda, NYU Abu Dhabi, and the Stellenbosch University. The motivation behind the Imagine Summer School is that apart from knowing how to use your MRI machine and knowing how to post-process the data and acquire information from the data, it's also very important to know how your machine works and how to maintain and upkeep your machine. It has been found that 14 to 19% of donated medical equipment from high-income countries is rendered non-functional when donated to low resource settings, because either from due to differences in compatibility, being that the energy grid is not compatible, or that there's not a team or people close by that can maintain the scanner or that can do the reparations if the scanner ever gets damaged. All these different causes lead to a lot of equipment being non-usable, and which points to the importance of having people that also know how the machine works and how to repair and maintain an MRI scanner. In the Imagine Summer School, we were building an MRI scanner for preclinical use. Was also done in the interest of time, but also because preclinical MRI is practically non-existent across Africa, and it would also be an interesting avenue of research that has not been explored yet. As we all know, the field MRI is an accessible point of care imaging tool. And yes, I said it's important to do capacity building. So here the motivation is exactly to do capacity building for hardware development, maintenance, and repair. In terms of accessibility, to demonstrate the feasibility of an open source low budget scanner build. It's important that it's open source also because a lot of scanners are often more open source on the software, not as much on the hardware. So here we are uploading all the CAD designs and whatnot online on GitHub so that it can be accessible to anyone and hopefully easy to replicate. The target audience here are medical engineers, MRI technicians, and computer scientists, but also people in veterinary science as well. So yeah, it's here as well a broad background. So this encourages interdisciplinary collaboration. Hopefully allows for more innovation through different worlds coming together. And yes, everyone brings their expertise and they're trained as a team and have to complete the different course deliverables together. So, like the other training programs, the Imagine Summer School also follows the Teach, Try, Use pedagogy. So here it is a 5-week online foundational course, self-paced as well. And then comes a 2-week build where the two low field scanners were built in parallel in two different sites. So one in Cape Town and one in Montreal. Some people were able to attend in person, and some people helped online through more of software-oriented things or helping with the design of a phantom and so on. Then in the use is a 2-week practicum, basically for debugging and data acquisition and processing, since, as you can imagine, building an MRI scanner in 2 weeks is not an easy feat. So there's plenty of debugging to do. So the 2025 pilot started in May this year, and we had 157 applications from 24 different countries, from which we were able to select 40 participants from 12 countries. Yeah, hopefully next year we can expand it a bit further. And the fields of expertise mainly came from radiography and imaging technology, biomedical engineering, computer science, and physics. So in the Teach block, the course content was provided on 4Waves, which is a platform that actually is used for all the camera training programs. It basically allows you to have all the information together in one place, and it's quite easy to follow. And then also all the seminars are uploaded onto the corresponding date, so people can easily join the Zoom session from there. So there was also not only online self-paced content, but also seminars and weekly tutorials that were provided on Zoom, like the one shown here. So then comes the 2-week on-site build lab, one in Cape Town at Stellenbosch University and one at the Neuro in McGill, which I also participated in. So the scanners are 50 millitesla scanner, and then as well as building the scanner, a robotic field mapping system was built, which was developed by one of the participants here, Sipan. of the Imagine Summer School, and it's also all the information for that is available on GitHub. So, of course, for a low field scanner, we're using a whole bag magnet. The magnet configuration was developed by Thielen here as part of his master thesis using a genetic algorithm optimization program to find the best configuration for a number of rings. Yeah. So ultimately, 11 rings were chosen, and we used neodymium magnets, 12 millimeter cube neodymium magnets, with the aim to build a 50 millitesla magnet. In practice, it was found to be 47 millitesla. Here we used a 3D printer for all the holders, and same for the gradients and RF coils to basically lower the cost. So here we have the magnet building process. Yeah. And then for the RF circuit, just a little bit of background. We have. So the way the RF circuit works is first we have the Marcos client. For the summer school, we use the Marcos control system, which is the one that we also use at Valencia. And essentially, this communicates with the red pitaya, which looks like this, which has an adapter to connect with the RFPA. And then this is the RFPA. This is a 1 watt RFPA, which is not the most powerful RFPA known, but for these applications for a small scanner and not too strong RF pulses, this should be plenty. Then we have the transmit receive switch, which was soldered and resoldered a lot of times. And then we have the RF coil. So then the signal is sent through the from the red pitaya through the RFPA through the switch to the coil, and then once you receive the signal, again the signal comes from the RF coil through the switch. Now on the receive side of the switch, the signal is then amplified by the low noise amplifier, comes back to the red pitaya, and then is visualized in the Marcos client. Oh, sorry. Oh, yeah, this is the LNA here. Then for the gradient circuit, the setup is similar. So first you have the Marcos client. Again, this sends the gradient pulses to the red pitaya. The pitaya is connected through this adapter to the GPA FHCO, which basically amplifies the gradient signals to the three different gradients for the X, Y, and Z components. And this is what they look like once they are winded. Then once we have all the different components built, we need to then integrate all the components together. This includes shielding from any possible noise sources through aluminum boxes. So you can see here that all the different components have their own little box to eliminate electromagnetic interference. And then we also have to build, of course, the field mapping robot, which looks something like this. This was used to measure the magnetic field homogeneity for both scanners. It was found to be 4,000 ppm over 6 centimeter DSV, which is for this volume not ideal, but we need to consider that there is currently no shiming. So once such shim is applied, hopefully this number can be brought down significantly. A very important part of the process is also noise reduction. If everything is not grounded correctly and shielded correctly, there will be a lot of electromagnetic interference. So the team, I was already gone. The team followed the steps characterized in this paper by Teresa Goyer Naval and Jethro Alonso, basically outlining what the necessary steps are to reduce the noise in a consistent manner. So this essentially allowed to reduce the noise from I don't remember the value, but hundreds of microvolts to about 40 microvolts, which, considering our Johnson limit here, is enough to get a clear signal. So we're still working on the signal generation. Yes, I said it's not an easy feat. So this is mainly focusing on testing for a wide range of frequencies. If you don't know the exact frequency that you're working at, it can be hard to find your Larmor signal. And also working with different phantoms. So for example, oil is being used instead of water, a smaller coil to count for to acquire a signal in a more homogeneous area of the scanner, and so on. So yeah, here are the main takeaways. Again, broadly coming to camera as a whole. Camera shows that community-driven initiatives can deliver impact despite limited funding. Hands-on training is particularly effective, and here as well, from a hardware side of things, it's a very hands-on training process. Low-field MRI offers a feasible, accessible route for capacity building. And with regards to the Imagine Summer School, we hope to next year be able to expand the summer school a bit further, incorporate all the lessons that we have learned this year, and hopefully have funding for more people to attend in person. Yeah, that's all from me. Thank you very much.